Looking to learn chemical energetics from a University of Cambridge graduate? Let's begin. Chemical energetics is one of those topics where a lot of memorization is required because a lot of new content from here on out will be covered, such as knowing what are the different types of enthalpy changes, and you will be introduced to this new concept called Gibbs free energy and entropy as well, and how all of these relate together. So we start off by trying to understand what is enthalpy. So enthalpy is the total chemical energy of a reaction or a substance. And when we talk about a change in enthalpy, we're talking about energy change in general. And the usual units is kilojoules per mole or joules per mole. And here we can see two typical reactions. So one of them on the left, this is an endothermic reaction. And this is because when you see the delta H, it is overall increasing from the reactants to the products. So there is a positive sign for this delta H. Now as for the right side, this is actually an exothermic reaction. And it is the exact opposite where the reactant's enthalpy decreases as the reaction proceeds into the product. And therefore the enthalpy change has a negative sign. So what's the point of standard conditions? Standard conditions is a very specific way for scientists across the globe to have the same set of conditions for a particular experiment. In this case, when we're trying to measure the enthalpy change of anything, let's say a reaction for example, scientists across the globe will have to use the exact same set of conditions, which is the standard conditions, and whatever values they get from the experiment, they can therefore say that this is the standard enthalpy change of whatever, let's say a reaction. So how are enthalpy changes experimentally determined? Well, scientists usually use this thing called a calorimeter. And this is a diagram, a very simplified diagram that you would probably get used to seeing when you head into the lab. And what basically happens is, in the lab, we can create a simple calorimeter by having a beaker and two stacked polystyrene cups with a lid, and you have your solution inside, or whatever reactants inside the cup reacting. And then of course, you need a thermometer to measure your temperature changes, and you need a stirrer to make sure there's even mixing in the solution. Now what's going to happen is, we will try to measure the temperature change of the reaction without it losing as much heat to the surroundings or to other parts of the experiment, for example the beaker. And that way, we can accurately determine the temperature change from the reaction, and from there, we can use the temperature change to calculate the enthalpy change. So here is a simple solution that you ought to memorize. Q stands for heat, and M stands for mass. C stands for the specific heat capacity, which is usually set at 4.18 joules per cm cube per Kelvin. And then next we have delta T, and this is just the change in temperature. Now, with Q equals negative mc delta T, you can find from the change in temperature the heat gain or heat lost in the experiment. And from there, this heat is usually in joules or kilojoules, and you can use that to equate to the enthalpy change itself. Now, of course, there are some assumptions to our calculations because our calorimeter isn't perfect. So we assume that there is negligible heat loss to the surrounding air, negligible heat loss to the calorimeter, and the density of the solution is the same as that of water. And that's why we usually use the specific heat capacity of 4.18 joules, because that is the specific heat capacity of water, and we have a solution. We just assume that the density is the same, and therefore the specific heat capacity of the solution is the same as water. And next up, whenever we do a practical or experiment with heat changes, we always have to do this thing called temperature correction, because we of course know that in reality, heat is actually lost to the surroundings, and as a result, we will need to account for that. So here's a typical graph that you would see, and with all the pointers of axes that you can see in black, right? One would normally draw a graph that goes something like this. But in order to determine what is the actual maximum temperature change, what you could do instead is draw a first line to show this initial temperature. Usually the initial temperature will be taken over a few minutes to equilibrate the temperature, and then after the reaction starts, you would want to draw this straight line down here, as you can see. So this straight line actually determines the maximum temperature increase of the reaction. And we would usually use this to go and calculate my enthalpy changes. So this is again to account for all the heat losses to either the surroundings or the calorimeter. Now I want to take some time to jump into what are the different types of enthalpy changes. So if you skip to the back, you'll see that I've listed a summary of all the enthalpy changes that you have to memorize. That's right, you heard me, memorizing all the enthalpy changes. It is really tedious, but I assure you that I don't expect students to memorize too much. But please, 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 for chemical energetics, you have to memorize it. And this is because you need all the knowledge of all the enthalpy changes in order to proceed in your theoretical calculations of enthalpy change. So starting from the top, we have the standard enthalpy change of reaction. For the reaction, this is, of course, you need to memorize the definition. This is the energy change when molar quantities of your reactants react according to a specified equation. And this is in their standard states and the specified temperature, of course. Usually you have to add this at the end whenever they ask for a standard enthalpy change of anything. And on the right, I have examples of such enthalpy changes accordingly, and I show you what is the typical sign for such reactions itself. If it's positive/negative, that means the enthalpy change really depends on the specific reaction. Next up is standard enthalpy change of formation. So for this is also regularly tested. This is when 1 mole of substance in its standard state, yes, take note, this is standard state, formed from its constituent elements in the standard states as well at 298 K. This is the usual temperature when I'm referring to the standard temperature. So a typical example is whenever I say I want to know the enthalpy change of formation of SnO2, right? I know the standard state is in a solid form, and from its constituent elements, so I would take Sn, which is naturally a solid because it's a metal, and we have O2. We have O, the element O naturally occurs as O2, oxygen gas. And after balancing my equation, which doesn't need any work for this one, we'll get our enthalpy change of formation. Next up is enthalpy change of combustion. So this is when 1 mole of my substance, only 1 mole of the substance, right, is completely burnt in excess oxygen, and all the reactants and products are in standard states. Of course, again at 298 K. So for example, you have butane. Realize that this is 1 mole, and by combusting an oxygen, I get all my reactants and products in standard states. So CO2 will be in gas, and H2O will be in liquid. And then I just balance my equation, and that's my enthalpy change of combustion. Next is enthalpy change of neutralization. So this is another special case because you need to know that this is when 1 mole of H2O is formed from the reaction, and at 298 K. So this is for a neutralization reaction. So an example is, let's say I have a equation between NaOH and H2SO4. I have no choice. I have to halve the mole of H2SO4 because only that way we can get 1 mole of H2O. So you must balance your equation accordingly to the conditions of the enthalpy change of neutralization. Next, bond energy. So we went through this before in previous topics. Bond energy is the average energy required to break 1 mole of covalent bond between 2 atoms in the gaseous state. So take note, this is in the gaseous state. So this is a typical example. Next is enthalpy change of atomization. So this is pretty much turning your elements from their standard states into the gaseous atoms. So here we have sodium, which naturally exists as a solid at standard state, and then we're turning it into a gas. You could also have gaseous atoms that come from a compound. So if it's from a compound, you're expected to get one mole of compound and turn it into a gaseous state. So for example, you have PbCl2, which is a solid, and I'm just breaking this down into the elements in their natural standard states at gaseous in their gaseous forms. So for example, it'll be lead gas and Cl2 gas. Then next, we have lattice energy. So lattice energy, you have one mole of solid ionic compound that is formed. Take note, it must be ionic, it must be a solid, and it's formed from its constituent gaseous ions. Very specific states, and they love to test this. Okay, so for example, K plus gas plus Cl minus gas, they will combine to form your KCl, and this is a solid. So take note of all these states. Then you have ionization energy. So this is also covered in atomic structure. Energy required to remove one mole of electrons from one mole of gaseous atoms to form one mole of singly charged cations. Take note of all the one mole and take note it's in the gaseous state, right? And then next is electron affinity. So electron affinity is a new sort of enthalpy change. It's actually the opposite of ionization energy. Instead of removing electrons, I am putting electrons into the atom. So in that case, you would pretty much expect that it would be negatively charged. And last two, we have enthalpy change of hydration. So this is pretty much dissolving an atom. So I'm dissolving anything in a standard state, one mole of that gaseous ion in the standard state, dissolved in water to give a solution of infinite dilution. Don't really need to know what exactly this means, just know that it's in the aqueous state. And it has to be one mole. And lastly, you have enthalpy change of solution. So that is when one mole of substance in a standard state completely dissolve to give a solution of infinite dilution at 298K. And this is, for example, sodium sulfate as a gas. You're dissolving it and making it aqueous. So they actually break apart in its ionic forms in the gaseous state. So again, I must emphasize that you must memorize all these enthalpy changes because they can ask you for any definition at any point in the exam and you have to recite it. You also need to know how to apply the definition. So if they ask for the enthalpy change of formation of tin oxide, for example, you would need to come up with it immediately and write the whole equation as well. Now, where is this applied usually? This is usually applied in the theoretical calculation of enthalpy change. So let me explain how this is relevant. When you are trying to calculate theoretically what is the enthalpy change, for example, from W to Z, the direct route would be the obvious choice. But when you don't have the direct route, or when you're trying to find out this delta H1, for example, the direct route, you can take an indirect route. So for example, you can do lots of side reactions from W to Z. So you can take an indirect route from W to X to Y to Z. And if you know all of these enthalpy changes, you can actually add them all up together and it would equate to delta H1 as shown over here. So you can imagine that a typical question would ask you how to calculate the direct route or the enthalpy change from a certain reactant to a certain product while giving lots of other side enthalpy changes that you can use to form the indirect route from your reactants to your products. And in order to do that, you need to know all the enthalpy change definitions and how to apply all of them to get all the equations of the enthalpy changes. Another side equation that you have to know is the relationship of bond energy to delta H. So usually, you can use the bond energies involved in a reaction to determine the enthalpy change. So the sum of all the bond energies of the bonds that have to be broken within your reactants, you can minus the total sum of all the bond energies of the bonds being formed in the products, and this will give you the enthalpy change of the reaction. So now we talk about a new concept, entropy. What is entropy? Entropy is usually defined as S, and this is the measure of randomness, the chaos, the disorder in a system. And you can think of it like the number of ways that you can distribute the energy in the system through the motion of its particles. So what are some of the factors that affect entropy? Well, a very obvious one is when there's a change in temperature. So if I increase my temperature, for example, the Ke of my particles will increase. So overall, the range of energies increase because every particle kind of gains a range of energies, and you just have more ways to distribute these energies, and therefore your delta S, or the entropy change, will increase from the change in temperature, which is an increase in temperature. Next is when there's a change in phase. So in general, if my particles move more freely, for example, if I go from a solid to a liquid, the particles get more disordered, more chaotic. This equals more ways to distribute energy, and therefore delta S increases. And you can also increase entropy through the mixing of particles. So if I mix it, the volume of each gas is increased, and therefore more ways to distribute the particles and energies. Now, I want to show you how delta H and delta S come together to influence this other delta, delta G. Delta G is the Gibbs free energy, and it's very useful in predicting the spontaneity of my reaction. So if delta G is less than 0, this means that the reaction is spontaneous. And if delta G is greater than 0, that means my reaction is not spontaneous. And I can just plug my delta H's and my delta S at a specific temperature to calculate my delta G at that specific temperature. And this is a very good gauge as to the spontaneity of a reaction. Of course, with a formula like this, there are limitations in predicting the spontaneity. For example, usually I would calculate in standard states, but we all know that whenever we're given a random context in a question, these are usually not as standard states, and therefore you can't really rely on the delta H or the delta S values that you are provided because they do not equal to the experimental conditions. Number two, the temperature can be different. So delta G or your delta H or your delta S actually are all influenced by temperature. And therefore, whenever you change the temperature, even more so from the standard state, you would not be able to predict as well the spontaneity of a reaction using delta G. And lastly, the most important consideration of them all, and perhaps the most powerful explanation, is that you can't predict kinetics using delta G. Delta G only tells you the thermodynamic stability. Yes, the thermodynamic stability. Very long word. But you can't tell how fast a reaction could go with delta G. So I'll give you an example. An example is actually diamond to graphite. This is actually thermodynamically possible, but we all know that diamonds last very long and would probably take centuries or thousands of years before they can be converted to graphite. And therefore, you can see that delta G actually doesn't really tell you any insight into the rate, because for this particular reaction, the rate is really, really slow. And you could even say that if it's too slow, it's not really spontaneous. And lastly, for this topic, I want to tell you about the effect of temperature on the spontaneity of my reaction. So usually, you would have to predict the sign of delta G with regards to the delta H, the delta S, and the temperature of the experiment. So here are a few permutations of my delta H and my delta S. So for example, if my delta H and delta S, my delta H is negative, but my delta S is positive, right? This means my delta G is negative at all temperatures. You can see that from this over here. Okay, since delta G equals delta H minus T delta S, and we know T is in Kelvin and is always going to be greater than 0. And because of that, you would know that delta G equals delta H minus T delta S is going to be negative in these conditions, and therefore is spontaneous at all temperatures. You can also say the same thing in the reverse, which is delta H is positive and delta S is negative. Delta G will be positive at all temperatures. and therefore it is non-spontaneous at all t's. Now it gets tricky when delta H and delta S are the same signs. If both of them are negative, you have to look at the magnitude of your delta H and your T delta S. Overall, if my delta H is lower than my T delta S, the delta G is going to be negative. And therefore, it is very dependent on temperature. So if my temperature is low enough, you can actually bring down the T delta S low enough so that overall, delta G is only negative when the temperature is low enough. Next, if delta H is positive and delta S is positive, the reaction will only be spontaneous at higher temperatures. Again, this is very dependent on the magnitudes of delta H and your T delta S. So that's all for chemical energetics. As I said during the lesson, I hope you will spend some time to sit down and memorize all the different enthalpy changes and their definitions and the ways to apply these different enthalpy changes of reactions. Next, I hope you would spend some time to also try to practice doing your theoretical determinations of enthalpy changes because that tends to get asked in the exams a lot. If you like this content, be sure to hit the subscribe button below so that you can get more frequent updates from this channel. If you want to enroll in my online class, be sure to hit the link below so that you can book a free call with me and I can run through with you your past exam paper and clarify any doubts and challenges that you have with chemistry and show you why my program is the best fit for you. I'll see y'all in the next lesson.